Use the data booklet to help you answer this question. It's about amino acids and peptide or amide links. So the first thing it says, draw the Zwitter ion formed by phenylalanine. So the first thing we need to do is go find phenylalanine on our data sheet. So we're in the amino acid section. We can see it here. So it's our amino acid section that we would normally see, which is this part. And then our variable R group is a CH2 and a benzene ring. Now then we need to remember that when we form a Zwitter ion, this is like internal ion, then the acid group is going to be a proton donor, the base group is going to be a proton acceptor. We're going to move one from one side to the other. So let's just go back. Remembering we had our regular, so our R group was a CH2 and a benzene ring. And remembering that was our H. We had a carboxylic acid group on one side, but it's going to act as an acid and donate its proton to our amine group on the other side, which acts as a base and accepts that proton, making sure that we got 1 plus and 1 minus Zwitter ion. Then it asks us to draw the structure of serine at high pH. So let's go back to our data sheet and find serine, where our R group is an alcohol, a CH2OH, an alcohol group. So we had a C with a H, it had a CH2OH. Alcohol groups don't react with acids or alkalis, so unaffected by the high pH. High pH means that you've added OH minus, which means we're going to remove acidic protons, which means that the carboxylic acid end is going to become an O minus. The amine end is going to stay as an amine. Then it says both dipeptides formed when phenylalanine, which we did the Zwitter ion of, reacts with serine, which we did the high pH. We're going back to what they were like before. So remember, a dipeptide, start with our amine group at one end. This part of a dipeptide will not change. So the peptide bond there, okay, so this would be a dipeptide's general structure. And then we're going to put our R groups down here. Now the point is that all we've got to do is swap around the R groups of phenylalanine and serine. So we've made our peptide link. So here's our peptide link. Yeah, this is our peptide bond between two amino acids. So what we're going to do is I'm just going to cheat slightly, which obviously you wouldn't be able to do in an exam. I'm going to copy that and I'm going to put another example of it down here. I'm just going to move it along. All I need to do now to make my two dipeptides is in one of them put serine on the left and in the other put serine on the right. And in the first one put the phenylalanine on the right. So remember, these are just the R groups for these specific amino acids, and then the other put it on the left. These are the two possible dipeptides. Just get rid of that. Let's go to the end of the question. 6.4. An amide link is also formed when an acyl chloride reacts with a primary amine. That can react because amine is a nucleophile because it's got a lone pair. And the carbon in the acyl chloride is delta plus. This mechanism, let's draw it out and then we can name it afterwards. So we've got CH3, CH2, C, double bond O, Cl. And then we've got our amine, in this case is CH3, CH2, NH2. So it's got a lone pair on the N. It's going to use its lone pair as a nucleophile to attack the delta plus carbon. So the first part of the name of our mechanism is going to be nucleophilic because we used a lone pair to attack a delta plus carbon. Now the weakest bond in the acyl chloride is the pi bond of the double bond. So that's going to break. So we haven't directly swapped, we've added it on to start off with. So at this point we've added something, so nucleophilic addition. The Cl's still there, and now the N's there, but now the N has made an extra bond. So it already had 3 bonds, and now it's got 4. So it's positively charged. Now the tip I would have is when you're drawing this intermediate, make sure that it has the 1, 2, 3 of the intermediate. So we have 1 lone pair, 2 charges and 3 curly arrows. 1 lone pair, 2 charges, 3 curly arrows. 1 lone pair here. We've got the 2 charges and then we're going to have the 3 curly arrows. So we're reforming the double bond, kicking out the chloride ion and kicking out a hydrogen ion. Now, because the chloride ion is negative, the curly arrow goes towards Cl, making it negative. And because hydrogen ion is positive, the curly arrow goes from the bond away from the H towards the nitrogen to get rid of that plus charge. So because we reformed the double bond, the oxygen is no longer negative. It's used those electrons to make the double bond. The chlorine's gone. We're now joined to just the nitrogen. It lost 1 H, so it still has 1. And it still has the ethyl group. But it lost its plus because we put electrons back onto it. So in this step, in the very first step, we added it. And then in the next step, we eliminated a H and a Cl. So we didn't just swap, we nucleophilic addition, elimination. And it wants us to name the organic product. So we have to find the longest carbon chain containing the functional group. So for those of you that don't know, this is the amide functional group. This is the carbon of the functional group. So the longest carbon chain containing the functional group is prop. And it's an amide. So it's propan because there's only single bonds between the carbons. And then it's an amide, so propanamide. And then attached to the nitrogen, we've got another 2 carbon chain, so it's called N-ethyl propanamide.